Hello everyone, and thanks for watching Edupedia World Videos. In this video we'll start a new topic, rotation of rigid bodies, and the first subtopic we learn is moment of inertia. Moment of inertia is the analog in rotational motion of mass in linear motion. We're now moving from linear motion to rotational motion, and we'll see that most of the quantities we saw in linear motion, like mass or force or momentum, they'll have their analogs in rotational motion. Right, so let's look at mass for a second. We know by Newton's second law that F equals ma. Right, so qualitatively, what is mass? We know that if the acceleration is the same for a number of objects, then the greater the mass, the greater the force that needs to be applied. If we need an acceleration of 1 meters per second square, then the greater the mass of the object, the more force we have to apply. Right, so the mass is sort of the tendency of an object to move. The greater the mass, the less tendency it has to move, the harder it is to move the object. Now, when it comes to rotational motion, the mass is not the only thing that determines how hard it is to move an object. There are other factors which we take into consideration, and when we take all of them into account, we arrive at a new physical quantity which is called moment of inertia. So just like every object in linear motion has a mass, every object when it is in rotational motion has its own moment of inertia. The greater the moment of inertia, the harder it is to move an object. Right? So why is mass not the only thing? What are the other factors that come into account? So let's look at a small example. I have an axis about which I am rotating objects with an angular acceleration alpha. Right, the two objects which I am rotating are two rods which are completely light. They don't have any mass, but at the ends of the rods we have small objects attached. We have a mass. The mass of both of them is 1 kilogram. One length is equal to 1 meters and the other length equals 2 meters. Right? And let's say we want to give them the same angular acceleration. Remember, we're taking the analog of linear motion. So in linear motion we took the same acceleration and we quantified mass. Here we are taking the same angular acceleration. So let's say we want to give both of them the same angular acceleration such that they complete their first circle in a time interval of t is equal to 1 second. Right? So that means in t is equal to 1 second, this particle has actually moved a distance 2 pi r. That is 2 into pi into 1. By the way, the circular motion is happening perpendicular to the plane of your screen, right? So both these objects are actually moving inside the screen initially. So this covers a distance of 2 into pi into 1 in 1 second, whereas this covers a distance of 2 into pi into 2 in 1 second. And we know that a is equal to alpha r. So for the same alpha, the farther the object is away from the axis of rotation, the greater the acceleration, right? The greater the force that is required to move that object. So now we see the difference. When it comes to force, mass is the only thing that matters, but when it comes to rotational motion, mass is not the only thing that matters. What is also important is the distance from the axis, right? So for the same mass, if we want to move it in a circle of a small radius, we need to apply a small force. Actually, that's not strictly true, because just like mass has an analog of moment of inertia, force has an analog in rotational motion which is called torque, which is quite similar to force but has some differences. We'll look at torque in detail in the next video. Right now we are looking at detail in moment of inertia. Right? So for different radii and for the same angular acceleration, just like we have acceleration in linear motion, we have angular acceleration in rotational motion. So for the same angular acceleration, we need to apply a greater force or torque in the second case than in the first case. So, and it also seems to us logical that the farther an object is away, the greater force or torque we'll need to apply. Right? So this is why we see that two things determine how hard it is to move an object in rotational motion: the mass and the distance of the object from the axis of rotation. For the same mass, if the distances from the axis of rotation are different, then for the same angular acceleration, we'll need to apply different forces or torques. Right? So I'm just going to give you the formula for moment of inertia right now. I'm not going to derive it. We'll look at that in detail in the next lecture. Right now our focus will be to learn the properties of moment of inertia and to learn how to calculate moment of inertia for different extended bodies. Remember, up till now we've only talked about particles, but now we'll not talk about particles, we'll talk about rods and we'll talk about spheres and so on, right? In advanced cases, you might even want to talk about objects like a cone. What if you wanted to rotate the cone about its axis, right? So now we are not dealing with point particles, we are dealing with extended objects. The formula for moment of inertia is this. For discrete objects, it is represented by I, just like mass is represented by m. For discrete objects, it is summation mi ri square, where ri is the distance of the ith particle from the axis. It's actually the perpendicular distance from the axis. For example, if this is an axis and this is an object, we'll take this to be ri, not this or this, right? So the perpendicular distance of the ith particle from the axis. So we have, let's say, a collection of many discrete particles, and we wanted to calculate the moment of inertia about this axis. So first of all, the first difference between mass and moment of inertia. The moment of inertia not only depends on the mass, but the axis chosen, right? So for example, in these cases, the moment of inertia of the second one would be greater than the first one because it's farther away, right? But if we take the axis instead of this point to be this axis, it's true that the moment of inertia of the second ball will be greater than the first ball still, but both of them will change because the distance from the axis is now maybe 2 meters and 3 meters, right? So the mass of an object is independent of any frame of reference or coordinates chosen, but the moment of inertia changes with the axis chosen. If you change the axis, the moment of inertia will change. And we see here as well, because if we take this axis, or if we take this axis, or if we take any other axis, Ri would be different, right? Let's just focus on this axis for now. So this is the axis about which we want to rotate a discrete collection of points. So we'll just take the mass of each of them, we'll take the distance from the axis of each of them, and we'll just add up mi ri square, and that will give me the moment of inertia, right? So in this case, let's say this is 0.5 meters. So the moment of inertia of this object about the first axis is 1 into 1 square, that is 1 mr squared, right? We have only one object, so we don't need to add. The moment of inertia of this mass about this axis is 1 into 2 square, that is 4. The moment of inertia of this object about this axis is 1 into 1.5 whole squared, and the moment of inertia of this object about this axis is 1 into 2.5 whole square, right? And that makes sense as well, because the farther an object is away from the axis, for the same angular acceleration, it would have a greater acceleration, remember this. And the greater the acceleration, the greater the force required, and force is a measure of mass for the same acceleration, right? So we see for a discrete system of particles, we just take the individual masses, we take the distances, perpendicular distances from the axis of rotation, we square that, multiply the masses and add them up. And the generalization to continuous systems is easy enough. It is simply dm times r square. So instead of a discrete system, if we had a continuous body, we'll take small elements, and for each element we'll take the perpendicular distance, and we'll take the small mass dm which the element has, multiplied by r square, and integrate in such a way that dm goes through the complete body. So we take every element into account, right? How this formula came about is, we'll see that in the next lecture, because we need the concept of torque for that. But right now, intuitively, I think you probably get it, why r is also important, why the distance from the axis of rotation is just as important as the mass, because the greater the distance, the greater the circumference of the circle, the greater the torque that must be applied, right? So let's start by calculating the moment of inertia of some bodies. I'm not going to do for discrete bodies except in one simple case, because it's easy enough, right? So let's say this is the axis of rotation. By the way, the greatest source of confusion in the beginning for students is this axis of rotation. So you must be clear, this object is going inside the screen and this object is coming out of the screen, right? They are not moving in this circle of the screen. The plane of motion is perpendicular to the plane of the screen, right? So if we have a light rod which have two objects attached at the end, the total length of the rod is L and the mass of each object is m. What is the moment of inertia? If the total length is L, this length is L by 2. So we'll have moment of inertia with m times L by 2 whole squared plus m times L by 2 whole squared. Moment of inertia of the first particle plus moment of inertia of the second particle, right? So that gives me ml squared by 2, which is the net moment of inertia, right? Now, what if I wanted to rotate this object not about the center but about this point, about this axis, right? In this case, we can remove this altogether. Let me just try to do that. So in this case, the left particle isn't moving at all. Like, it's hinged. Just like the hinges in a door do not move at all when you move the door. So this particle doesn't move at all. In fact, its moment of inertia will be 0 because the distance from this axis is 0. The distance of this point from the axis is L. So in this case, moment of inertia will simply be 0 plus ml squared. So that will be ml squared. So we see the moment of inertia in this case, when we rotate it about the axis at the end, is twice the moment of inertia when we rotate about the axis at the center. Thus, we make the conclusion that it is harder to move this object through this axis than it is through this axis. Now that would make sense to you intuitively as well, as if we move it through this axis, though one object is not moving, the heavier object is moving in a much bigger circle, and since mr square is a moment of inertia, r is the more dominant term. If we take it in the middle, yes, both the objects are moving, but the radius of the circles are smaller, right? So when we calculate it net, we find out that it's easier to move it about that axis in the middle than about an axis at the end, right? Let's look at continuous systems now. So the first simplest case we look at is a rod which we rotate about an end. So we have a rod of total mass m and total length L, right? Remember, now this m is not the mass of an object attached at the end of the rod. This m is the mass of the total rod itself. So in this case, we'll need to integrate. The best way to do it is, I'm just going to put this arrow every time to show you what is the sense of the rotation. So at a distance x, we'll take a small element of length dx. We'll write the moment of inertia of this small element, and we'll take the limits of x going from 0 to L, and that will add up the moment of inertia of every small element and give me the total moment of inertia of the rod. By the way, moment of inertia, a scalar. We are not talking about directions at all, right? So moment of inertia of individual things can be added up to give the total moment of inertia. So di, which will be the differential moment of inertia of this small element, will be dm times x squared. For dm, we need to calculate the mass per unit length, which is m by L. That is the mass per unit length. So m by L into dx will be dm, right? The mass of this object. So that will give me m by L dx x squared. We can integrate it to get the total moment of inertia. X will go from 0 to L. X squared dx will give me x cubed by 3. So that will give me ml cubed by 3 and L will cancel. So I get I is equal to ml squared by 3. Now these standard formulas you do need to remember, it will be helpful, but for greater knowledge you need to know how to derive them, right? So that is the moment of inertia of an extended rod if I want to rotate it about the center, right? What if I wanted to rotate it about an edge? What if I wanted to rotate it about an axis at the center? Well, in that case, everything will be the same, except our limits, instead of going from 0 to L, will go from minus L by 2 to L by 2, right? Because if this is the axis, we take x at dx, x goes from minus L by 2 to L by 2, right? And what will that give me? This is ml cubed by 3 and 2 will give me 4, so it will ultimately end up giving me ml square by 12, right? So again we see that to rotate an object through the center is easier than to rotate an object through the edge, right? You can try to verify this at home and I'm sure you'll get the same result. X squared dx will integrate to be L cubed by 3, right? And we'll take L by 2, that is L squared by 4, right? And divided by 3, so it's L squared by 12, right? Thank you. Right? So let's take two more examples standard. One of them is an easy one. We'll take I apologize for my drawing the circles. We'll take a ring and we're rotating it through an axis perpendicular to the plane. So in this case, the whole ring will be moving like this, right? And the axis is drawing perpendicular to the plane of the screen, that is inside the screen or outside, right? So in this case, this is the axis and every point on this ring is at a distance r from the center. So we'll just have to sum of delta m of each of them, r squared, but r is the same, so it will give me mr squared, right, if the total mass is m. So for a ring it's easy enough because every particle of the ring is at the same distance r from the center, right? The more difficult question comes when we talk about a disk, right? Sorry. So now the question is different. We're talking about a disk. A disk means it has mass everywhere, right? It is not just the points at the end, but every point is there. Now this point or this point is not at a distance of r from the center. It is at a smaller distance, right? So in this case the answer will be different. And how will we calculate this? We'll take our elements to be differential rings, and we know the moment of inertia of a ring, and we'll integrate it to get the total moment of inertia. So this is our element now. The element is a ring of radius r and thickness dr, and the total radius we'll call it capital R, right? So moment of inertia of this differential element will be dm times r squared. For dm, we know that the total mass per unit area in this case is m by pi r square. So dm will be m by pi r square into the area of this ring, that will be 2 pi r dr. This should be capital R, I'm sorry, right? Because total mass per unit area, we'll need to take the total area, right? So from this we get di equals r squared times m by pi r squared 2 pi r dr, right? And we integrate this and r goes from 0 to capital R. So we see pi and pi cancel. We get 2m by r squared times r cube will integrate to give me r to the power 4 by 4 from 0 to r to the power 4 by 4. So it gives me m r squared by 2. So the moment of inertia of a ring was mr squared, but of a disk is mr squared by 2. Which means that the disk is easier to rotate than the ring of the same mass, which seems intuitively to make sense, because if we have a disk, then we have some objects moving in a circle of radius capital R, and other objects are moving in a smaller radius, right? However, if we just pull these masses apart, we start making a small hole and we just push these masses outside and push them all to the edge, then every single particle is moving at a circle of radius capital R. So in this case we would need to apply a greater torque, right? So it makes sense to us that a disk should have a smaller moment of inertia than a ring, right? Others also you can try to calculate. For example, if you take a hollow sphere, the moment, and now this is a sphere, three-dimensional sphere, and you take an axis about the center. I apologize for my drawing there. If you take an axis about the center, the moment of inertia will be 2mr squared by 3, right? And the integration is slightly more difficult. You can look it up or try it if you want. And this is the way you can try to calculate moment of inertia over different objects, right? Now there are two small theorems which help us in calculating the moment of inertia for some objects, right? So we'll discuss them now. The first of them is the parallel axis theorem. And when this is used is, if we want to calculate the moment of inertia of an object and we know the moment of inertia of that object about an axis parallel to this axis but passing through the center of mass. So for example, if this is my three-dimensional object, let's say this is the center of mass of the object, right? We know how to calculate center of mass, we've seen that earlier. Let's say this is the axis about which I want to rotate the object. So this whole object will move like this, right? And this is an axis which is parallel to my original axis but passing through the center of mass. So the parallel axis theorem says that the moment of inertia about this axis will be equal to I with respect to Cm. Remember, the convention we used was V of A with respect to B, right? So A slash B means A with respect to B. So I of, when I don't write anything, it means D for the body. So I is equal to I with respect to the center of mass plus M D squared, where M is the total mass of this object and D is this perpendicular distance, right? I'll prove this now, but this is a theorem which helps us a lot of the times to find the moment of inertia, right? So for any object, let this total distance be R, let this distance, be R Cm, R with respect to Cm, and this distance be D. So we know that R is equal to R with respect to center of mass plus D, right? I for us will be summation of mr squared, right? MIRI squared. So summation m will add up to m if the other things are the same. In this case, this will be R with respect to center of mass plus D whole squared. Right, we can expand it. A plus B whole square is A square plus B square plus 2AB. So this gives me summation of mass times R with respect to Cm squared plus summation of mass and D squared plus 2 times summation of M R with respect to Cm D. Right, now the first term M R with respect to Cm whole square is just the moment of inertia about the center of mass, right? Because the moment of inertia about the center of mass will be, you take the small mass, you take R with respect to Cm, you square it and you multiply them and add them up. Summation md squared will give me capital MD squared, because D is common, we can take it outside. Summation m will give me capital M, and this term will equal to 0. Why? Because D can be taken out, and summation mi into R with respect to center of mass will actually give me the location of the center of mass, right? But the location of the center of mass with respect to the center of mass is always 0. You can look at it in this way. If we take MIRI for this object, and we take MIRI for this object, and we take MIRI for this object, and for this object, and we add them up, we'll get the total mass multiplied by the position of the center of mass. But that is 0 with respect to the center of mass, right? So this term will add up to give me 0. So this is how we can prove the parallel axis theorem. An application of this theorem would be, let's say I have my semicircular disc, but I want to rotate it not about an axis passing through the center and perpendicular to the plane of the screen, but about an axis passing through this edge and perpendicular to the plane of the screen, like this, right? So what is the moment of inertia? Well, it will simply be mr squared by 2, which is the moment of inertia about the center of mass, plus mr squared, which is the md squared term, right? So that will give me 3 by 2 mr squared. Right, so I could calculate the moment of inertia about an axis passing through the center of these two, right? So in this way, if I know the moment of inertia about an axis parallel to the unknown axis passing through the center of mass, then I can calculate the moment of inertia about the unknown axis, right? The second theorem, the first was the parallel axis theorem, the second is the perpendicular axis theorem. Now, the parallel axis theorem is always valid, but the perpendicular axis theorem is only valid in a special case, that is for planar objects only. So you can apply it to a rod, you can apply it to a disc, you can apply it to a ring. You cannot apply it to a sphere, however, because a sphere is not a plane object, it is a three-dimensional object, right? So the perpendicular object the perpendicular axis theorem says if you have now this is a two-dimensional object, remember, right? And let's say you have an axis like this, right? And you take two other perpendicular axes which are in the plane, right? So let's call this the x-axis, the y-axis, and the z-axis. The body is in the xy plane, right? So the parallel perpendicular axis theorem simply says that Iz equals Ix plus Iy. That is, the moment of inertia about the z-axis is equal to the moment of inertia of the x-axis plus the moment of inertia about the y-axis, right? How do we see that? So let's take any point. It obviously has coordinates xi, yi and 0, right? This is where we are using the fact that it's true for plane objects only, because the z-axis component will be 0, right? So the moment of inertia will be summation m times moment of inertia about the z-axis will be summation m times this distance whole squared. But this distance whole squared is simply mxi squared plus yi squared, right? Because this distance is root of xi squared plus yi squared. So we can add this up and we can directly see that this is equal to ix plus iy. Right? So what can be a use of this? Let's say we are talking about a semicircular disk again. We know the moment of inertia about the axis perpendicular to the screen, that is mr squared by 2. What if we wanted to find out the moment of inertia about this axis that is in the plane of the screen? I'm rotating it like this. Well, we know that the disk is a plane object, right? And by symmetry we know that the moment of inertia about this axis and the moment of inertia about this axis have to be the same, right? And we know the moment of inertia about the z-axis, that is mr squared by 2, right? We know that is equal to ix plus iy, and ix and iy are equal by symmetry. So this gives me equal to 2ix, which means ix is mr squared by 4. So now, without actual calculation, we've seen the moment of inertia of a disk about an axis passing through the diameter, right? So one small last concept left for moment of inertia, and that is a concept called the radius of gyration. Sorry. And the radius of gyration for any object is equal to, the radius of gyration of any object is equal to k if the moment of inertia is mk square. The radius of gyration is nothing but another way of telling the moment of inertia. For example, if you have a disk, the moment of inertia about this axis is mr squared by 2, right? So if we were to write it as mk squared, that gives me k equals r by root 2. So I could specify the moment of inertia in two ways. I could say we have a disk which has a moment of inertia of mr squared by 2, or I could say in the question we have a disk which has a radius of gyration of r by root 2. The radius of gyration of r by root 2 simply means the moment of inertia is mk squared, right? So if we have a rod and I'm moving it about an axis, then the moment of inertia is ml squared by 3. We calculated it a little bit earlier, right? If we were to write it as mk square, that means k equals L by root 3. So in other words, instead of giving the moment of inertia, I could give you k, right? Let's say I wanted to calculate the moment of inertia or specify the moment of inertia about any random axis. I could actually give you the moment of inertia, or I could just say this is an axis such that the radius of gyration about this axis is r by root 5. And all that is saying is that the moment of inertia about this axis is mr squared by 5, right? So the radius of gyration is, if you want to look at it qualitatively, it is the radius of an object in which every particle is situated at the end, which would have the same moment of inertia as this object, right? So if the radius of gyration is given as k, then the moment of inertia is mq square. It's as simple as that. This completes a moment of inertia for now it might have seemed like a little bit abstract topic to you because we don't know where it came from. In the next lecture we'll talk about torque and we'll derive these formulas about moment of inertia. Thank you.